you can find your talk here. All right, well, our last talk of the session today is back to our Leo conference founder, Paul Callis, who's going to talk about fireworks collisionally around Fomalhaut. He's been studying Fomalhaut even longer than he's been instigating this conference series.
Yeah, that's true. I'm going to show some new results. I mean, I was shocked by what I saw with Beta Pic from the MIRI team. I mean, it's like Game of Thrones in here. It's like, what's going on with these disks? And there's a lot of saga and drama with Fomalhaut. So let's do an episode recap. You've got, back in 2004, 2005, with the Hubble Space Telescope, with the Advanced Camera for Surveys, I resolved the in-scattered light in the optical, the dust belt at 133 AU. Oops. Let's go back and let's use it. Does that work? So at 133 AU, you have a sharp inner edge for the dust belt. And it's also offset from the star. This was a very clear offset from the star, 15 astronomical unit offset. And that's why in debris disk science we have the so-called stellocentric offset. Fomalhaut was the perfect example where you have a secular perturbation by eccentric planet moving the dust belt into an eccentric configuration around the star. So we had this hypothesis of a planet orbiting Fomalhaut, an eccentric planet, and in 2008 we imaged in 2 epochs Fomalhaut B, an eccentric Fomalhaut B. But this was a mysterious object. It puzzled us, and in that original paper we said, you know, we did some follow-up with some deep imaging with Keck and Gemini and didn't detect it. And it was detected in the optical, though, at 3 wavelengths, so we figured it had some component of reflected light. And in our paper, we studied 2 possibilities, a giant catastrophic collision between planetesimals or a circumplanetary ring system that was reflecting light. We said this is more likely because a giant ring system is long-lived, whereas collisions between planetesimals are rare and also short-lived. So the chances that I would happen to observe a collision around Fomalhaut were very small. So we favored the more long-lived hypothesis. And there was debate about this. Some papers championed the collision scenario. Other papers championed the planet scenario. And the nice thing is it's a testable problem. Over time, an unbound dust cloud will shear and start spreading out. So we needed just a bit more time to see what was the truth about Fomalhaut B. In 2020, Andras Gaspar and George Ricci analyzed the data in the Hubble archive and concluded that it was most likely a planetesimal collision because they found that Fomalhaut B was expanding in size, was becoming fainter, and disappeared in 2014. Again, they did point out the problem that it's short-lived, it's only a 10-year phenomena, and in their paper, it only happens once every 100,000 years. And yet, we weren't sure if this result was accurate because in 2013, where they see an extended result for Fomalhaut B, when we analyzed the same data with JSON, we found it to be a point source. So we had some disagreement there, but we did agree that the astrometry was not what we expected at all. It was a huge surprise. Here's the astrometry for Fomalhaut B from 2004 to 2006, and so there's a two years between these astrometric points, and here's 2 years between these astrometric points, and this is what. I'm going to use the green laser pointer. Is that okay for people? Yeah. For maybe, I don't know if it's the online, if they can see it. So right here, in 1 year, we see the same displacement as we did before in a 2-year interval. So just by eye, you can see the acceleration from 2012 to 2013. A really nice exercise that made this even more interesting is to deproject the sky plane astrometry to the face-on deprojected view of the system, assuming the Fomalhaut B is in that plane. And you can see this sort of curvature where at first, when we discovered Fomalhaut B, it has a eccentricity of 0.1, but then later it seems to be 0.9, and then it's like on a radial orbit. So what object will curve around like that? And that was consistent with this part with radiation pressure blowout of grains, but this part was consistent with a planet. So to solve this mystery, we proposed to do a deep image of the Fomalhaut system. A lot of the problems with Fomalhaut B is a low signal-to-noise detection, and so that's why the literature disagreed on the photometry, the morphology, and the astrometry. So we said, okay, let's just do a deep image and get to the bottom of this. So we proposed and had approved 24 orbits, which were double the integration time, or the number of rolls you can have compared to previous epochs. We're using the STIS coronagraph aboard HST, the 2.5 arcsecond wide segment of the occulting wedge. We're intentionally saturating. These are 30-second exposures because we're not interested in this region. Fomalhaut B is out here at 13 arcseconds. And so our goal was to solve the mystery of Fomalhaut B. But the result was something different. We didn't detect Fomalhaut B, we detected a new Fomalhaut B. It appeared out of nowhere. We know what's in the system from previous epochs. That point source was not there before at that location. The Fomalhaut B was here. So initially we called this Fomalhaut B2. There's B1, B2, but then it was pointed out in designations, a 1 and a 2 are subcomponents of something else. So we came up with circumstellar source 1. So it's kind of agnostic. It's a source. So it's open to further theoretical interpretation. So Fomalhaut B became CS1. This is CS2. And it wasn't there in any previous observations. We did not detect CS1, unfortunately, because 10 years had passed, and if you remember that acceleration, Fomalhaut CS1 might be around here, 50 AU farther from when it was in 2013, and half as bright, It's possible with the deeper observations we expect to make this coming summer, we might recover Fomalhaut CS1. Here's a comparison of where CS1 was in 2012, and you can see that at the location of CS2, which is like roughly here, there is no point source. It appeared in these intervening years. And it's funny that they're roughly in the same location. We're sensitive to CS1, CS2 sources of around roughly 160 degrees of azimuth around the star, but they both appeared in this region. The way we showed that it's a real detection is we split the team up into 4 independent groups. We all reduced the data separately, and we have 4 different, using different software, different methods. So we have the detection of CS2 is between SNR of 7 to 9, so we're confident it's real. So what are the implications? So planets don't just appear out of nowhere. So it must be true that Fomalhaut CS1 and CS2 are a catastrophic collision between planetesimals. Given the brightness of each event, and they're roughly equal brightness, you can estimate the mass of dust that is needed to scatter the light. And what's interesting in the animation is that if you notice, there's something particular about this. The dust cloud was kind of dark. So what we're saying is that the dust cloud at the beginning is optically thick. And and it's expanding, but it continues to be optically thick. And it actually looks like a planet. the dust cloud is only seeing light, starlight on the star-facing side, and the rest of the cloud is dark. After 8 years, it expands to an optically thin configuration, and all of a sudden, it starts getting pushed outward by radiation pressure. So what's amazing also is this 20-year timescale. This, of course, is just animation that, if you speed up the clock over thousands of years and compress it into a few seconds of video, this planetary system is sparkling with these collisions. In fact, over its lifetime, there are 22 million such collisions. So this has some interesting implications for us to think about, that, for example, these dust clouds can masquerade as planets, and not just briefly, but for an extended period of time. So when you look at Roman and Habitable Worlds Observatory, you have to understand how would you distinguish between this optically thick dust cloud, which has phases just like a planet does, versus a true planet. And also interesting is the motion, that when you look at your data and you see, we're always testing for common proper motion and orbital motion, but what Fomalhaut CS1 and CS2 are showing us is radial motion is a possibility for a companion or an apparent companion in a planetary system. We have follow-up observations with JWST. STIS doesn't have filters, so we're relying on NIRCam to test for comparisons to refractory objects in the solar system, such as this spectrum of Dimorphos, which shows absorption feature in a very red slope here, versus an icy spectrum, which would show absorption features at 2 and 3 microns. And we're also following up with HST. Here is some preliminary work. This GIF is showing 2023, 25, 26. I mean, 23, 24, 25, 3 years. So we think we see a northward motion. All of this is preliminary. We're working on the data as we speak, in a sense, with my co-authors here. So there's much more work to be done. Our estimates for the size of the parent bodies and the type of collision is very basic. It's just a few paragraphs in our paper. Entire investigations could follow up on what kind of collisions these are. Are they catastrophic? Are they erosive? And what is the dynamics of the system that would have all of these two events happen at the same location? So here's I'm out of time. Here is what I just talked about. I think it's very interesting. If you were not paying attention, here is the take-home point. We finally discovered the true identity of Fomalhaut B. It's a dust cloud. Now, what was destroyed is up to interpretation. All right, thank you very much.
Thank you, Paul. Do you have any idea how many 30-kilometer planetesimals there need to be in the system?
Yes,
in order to collide every 10 years and produce this?
Yeah, that's the part of the calculation. It's in the size distribution up to 300-meter sizes.
But is it crazy how many of them you need? Or?
No, it's not crazy. It's a normal disk, actually. It's a normal disk, yeah.
Okay, questions? Yeah. Oh, sorry, here, go ahead. Yeah.
Hello? Oh, great. Really interesting talk. Have you also considered the possibility that this is like a larger object that we can't detect, but it's getting slammed in its orbit every 10 or 20 years as it's sort of plowing through the inner edge of the disk? Would that change any of these observations?
There are other possibilities. This was published in Science. I don't recommend it ever. Whoever's publishing, somebody said they had something in Science. Don't. And talk to me, I'll tell you. They made us delete a whole paragraph, which was about, I had speculation that, for example, Pluto's Planitia basin was a 100-kilometer object that hit Pluto to create that. So you could have, for example, a dwarf planet that is impacted just like Pluto was, and now you have maybe a bound dust cloud So with CS2, it may never start going on a radial orbit if it's bound to its parent body, and that's what we would be testing over the next few epochs.
Okay, let's go to the question in the back first.
Yeah. So Paul, first, congratulations again on publishing this in Science. You know, it can be a fun ride. So my question is, where do we go from here in terms of understanding these things as classes of objects? So, like, there are some debris disks observed with HST that are on the order of like 10 arc seconds or so in size. Is it worth trying to reprocess the entire ACS disk pipeline archive to see if you can constrain some sort of meaningful limit on these types of systems, or what do you think is the next step?
It is possible. What can you do? I just mentioned check old data for radial motion, except you kind of have to have a good cadence, because if you don't have a good cadence, you have something that looks like a speckle here, a speckle there, and you can't really, you say those are uncorrelated or unrelated speckles, but if it's like with good cadence, you're tracking a radial motion, you have a dust cloud moving out radially, for example. Another mystery is, remember the cat's tail for beta pic? Why isn't there a cat's tail for CS1 and CS2, for example? That would be an interesting follow-up paper.
Okay, the last question, Chris.
Hey, Paul. Wonderful talk. I'm so satisfied to have this answer. I think it's clear that our community, a decade or two ago, thought that these collisions were so unlikely that we favored steady-state, solutions, and now we're realizing that no, we are witnessing individual collisions occur, and like you just said, this appears to be a normal-sized object, and the likelihood of it colliding is reasonable. One of the things we noticed when we were analyzing the beta pic data and trying to estimate, how large of a body could create the cat's tail, is that the actual mass of the progenitor is wildly uncertain, because all the mass is contained, of course, in the largest grains, which you don't observe. And so any of these estimates as to how likely this occurs are wild extrapolations. So I guess I was wondering if you could comment on your initial point, when you first published this paper, how you thought it was such an unlikely event, and now you've come around to thinking, oh, it's actually very likely. What changed in that analysis?
Well, the evidence is telling us what we should be thinking, right? What you just said reminded me of something else I wanted to talk about, though, related, is in the paper, and the theory was conducted by our collaborator Mark Wyatt at Cambridge. I want to give him credit for that. But in his idea of what's colliding, it's not the mass of the object necessarily that's important. In our paper, he's saying that these planetesimals are always being bombarded by smaller objects, creating a regolith, a deep regolith of dust. And I compare it to like the sugar cookies you have at Christmas. Like if you sneeze on them, the dust goes everywhere. As soon as these objects, no matter what size they are, collide, they release quite a bit of dust just from their regolith.
So binding energy is sort of... Yeah.
The rubble piles, but it was actually the top layer. That's what made in his calculations. Fomalhaut beat CS2 has been impacted 900 times already, almost 10 to the 3 times, before this much more energetic collision releases all the sugar coating everywhere.
Nice, thank you.
Okay, we have the final answer. Fomalhaut B is a sugar cookie. Thank you. Thank you, Paul, and thank you to all the speakers this afternoon.